Assalamualaikum warahmatullahi wabarakatuh, and hi everyone. Now we will discuss chapter 6, which is chemical equilibrium. But before we start, let's take a look of its learning outcome. So these are all the learning outcomes that you should know in this topic. But in lecture, we will only focus on C1 and C2, which are remembering and understanding levels. Okay, we start with dynamic equilibrium. So at the end of this lesson, you should be able to explain the following terms: reversible reaction, dynamic equilibrium, and law of mass action. The first term is reversible reaction. Actually, only few chemical reactions proceed in only one direction, or in other words, is irreversible reaction. Example, A plus B produce C plus D. As you can see, this reaction is written with an arrow pointing towards the direction from left to right, which implies that the reaction goes to completion. Means the reaction will stop when reactant is completely converted to product. But most chemical reactions are reversible, which takes place in both forward and reverse direction, at least to some extent. Reversible reaction never go for completion. Now consider this equilibrium system. A is the reactant, while B is the product. The double-headed arrow in the equation indicates as reversible reaction. So what is reversible reaction? Again, the reaction which takes place in both forward and reverse direction. So what is forward reaction? Reaction that proceeds from left to right. Left to right. While backward reaction is the reaction that proceeds from right to left. Right to left. How do reversible reactions work? So now, consider the decomposition of hydrogen iodide gas to hydrogen gas and iodine gas. When hydrogen iodide gas is initially introduced into the reaction vessel, only the forward reaction occurs. As soon as some hydrogen gas and iodine gas are formed, the reverse reactions begin. As time goes on, the forward reaction slows down because the concentration of hydrogen iodide decreases. As more and more products are formed, the reverse reaction becomes faster. At certain time, T1, the forward and reverse reaction occur at the same rate, and the mixture in a state of dynamic equilibrium. Now look at the graph of the concentration of hydrogen iodide gas, hydrogen gas, and iodine gas against time. Here is at initial condition of the concentration of hydrogen iodide. So we can see the concentration of hydrogen iodide decrease with time. This is at initial condition of the concentration of hydrogen gas and iodine gas. So the concentration of hydrogen gas and iodine gas increases with time. But after time T1, the concentration of hydrogen iodide and hydrogen gas and iodine gas remains unchanged. The system is in the state of dynamic equilibrium. The second term is dynamic equilibrium. Equilibrium is a state in which there are no observable changes as time goes by. So we have two types of equilibrium. The first one is physical equilibrium and the second one is the chemical equilibrium. So what is dynamic equilibrium? Dynamic equilibrium is a state when both the reactant and product concentrations stop changing because the forward and reverse rates have become equal. So, rate of forward reaction is equal to the rate of reverse reaction. Now, consider this new equilibrium system, the decomposition of dinitrogen tetroxide N2O4 to nitrogen dioxide NO2. At T1, the equilibrium is a dynamic equilibrium. Means after T1, the reaction did not stop, but the rate of forward is equal to the rate of reverse. There is no net change in the concentration of NO2 and N2O4 after T1. But it does not mean that the concentration of NO2 is equal to the concentration of N2O4. Okay, let's say the initial concentration of N2O4 here is 1.0 molar. After T1, it might be reduced to 0.5 molar, while NO2 starts at 0.0 molar, increase to 1.5 molar. So, definitely 0.5 molar is not equal to 1.5 molar. Now we move to type of equilibrium. The first one is physical equilibrium. For example, physical change of water molecule. So the number of H2O molecules leaving from liquid phase to gas phase is equal to the number of H2O molecules of gas phase returning to liquid phase. So keep in mind, physical equilibrium only involves in phase change. Next is chemical equilibrium. We learned that most chemical reactions are reversible. For example, dinitrogen tetroxide N2O4 is a colorless gas, while nitrogen dioxide is brown. At equilibrium, we know that the rate of forward is equal to the rate of reverse. This can be seen when the gas change from colorless to brown. Okay, how it happened? When we introduce some N2O4 gas into a sealed flask kept at 100 degrees Celsius, a change occurs immediately. The colorless liquid vaporizes and the gas begins to turn pale brown. The color slowly darkens, but after a few moments, no further color change can be seen. Okay, look at this experiment. At A, N2O4 starts to form NO2. So, the mixture is slightly colorless. At B, the mixture becomes pale brown. So at this time, more NO2 form. At C, the mixture reach final color, which is dark brown. So this reaction reach equilibrium at this time. At D, the concentrations and color remain constant. So the dark brown color remain. The last term is law of mass action, also known as equilibrium law. It can be defined as for reversible reaction at equilibrium and a constant temperature, a certain ratio of reactant and product concentration has a constant value. The K is the equilibrium constant. Or, for a particular system and temperature, the same equilibrium state is attained regardless of how the reaction is run. Consider this general reaction equation for reactant and product. So the equilibrium law can be written as K equal to the concentration of product raised to some power of Y is divided by the concentration of reactant raised to some power of X. So if we have the reaction of A plus B produce C plus D, and the small letter A, B, C, D is stoichiometric coefficient for the reaction species of A, B, C, D. Means A mole of A, B mole of B. So at equilibrium, K is C concentration to the power of C, D concentration to the power of D is divided by A concentration to a power of A and B concentration to the power of B. Example, now we have 1 mole of N2O4 produce 2 mole of NO2. So the equilibrium law can be written as K equal to the concentration of NO2 to the power of 2 divided by the concentration of N2O4 to the power of 1, where K is the equilibrium constant. So now we have table 14.1. This table shows the experimental data for the decomposition of N2O4 into NO2. So the ratio of concentration at equilibrium has a constant value regardless of the initial concentration of reactant and product. Exercises. So please answer these questions to achieve the learning outcomes of this subtopic.